In our last discussion, we explored how machine learning models learn during training and make predictions during inference. But what exactly do these models learn from? They learn from features, which are essentially the measurable properties or characteristics of the data. Often, the raw data we collect isn't directly suitable for a machine learning model. This is where feature engineering comes in. It's the art and science of transforming raw data into these more meaningful features, making them ready for a model to learn from. Feature engineering is critically important because the quality of your features directly impacts the performance of your machine learning model. Feeding raw, untransformed data to a model is like giving it a puzzle with half the pieces missing or upside down. The model might struggle to find patterns, leading to low accuracy and poor predictions. By carefully crafting features, we can help the model see the underlying structure in the data more clearly, enabling it to learn more effectively and achieve significantly better results. One crucial aspect of feature engineering is feature selection. Imagine you have collected a vast amount of data, resulting in hundreds or even thousands of features. Not all of these features will be equally useful. Some might be redundant, others entirely irrelevant, and some could even be noise. Too many features can confuse a model, causing it to focus on noise rather than true patterns. This often leads to a problem called overfitting, where the model performs well on training data but poorly on new, unseen data. By carefully selecting only the most relevant features, we can simplify the model, reduce the risk of overfitting, improve its interpretability, and often speed up training. There are several strategies for feature selection. Filter methods evaluate features independently of the machine learning model, often using statistical measures like correlation with the target variable, or simply removing features with too many missing values. Wrapper methods are more computationally intensive. They involve training a model on different subsets of features and selecting the subset that gives the best performance. Think of it as wrapping the feature selection process around the model training. Finally, embedded methods perform feature selection as an integral part of the model training itself, where the model algorithm has built-in feature selection capabilities, such as lasso regression or tree-based models, which inherently assign importance to features and can effectively ignore irrelevant ones. Beyond selecting existing features, we can also perform feature extraction. This involves transforming or combining existing features to create entirely new ones that might be more meaningful or represent the data in a lower dimensional space. For instance, if you have features for length and width, you can combine them to create a new feature called area, which might be much more predictive for certain tasks. Another powerful extraction technique is Principal Component Analysis, or PCA. PCA can transform a set of possibly correlated features into a smaller set of uncorrelated features, called principal components, which capture most of the variance in the original data. This effectively reduces the dimensionality while retaining valuable information, helping models to learn more efficiently. Feature mapping, or feature transformation, is another critical part of feature engineering, especially when features have vastly different scales or distributions. Many machine learning algorithms, particularly those relying on distance calculations or gradient descent, perform much better when features are on a similar scale. Without scaling, a feature with a larger numerical range might dominate the learning process, irrespective of its actual importance. Common mapping techniques include min-max scaling, which transforms features to a specific range, usually between 0 and 1, and standardization, which transforms features to have a mean of 0 and a standard deviation of 1. These transformations ensure that all features contribute equally to the model's learning process, leading to faster convergence and more stable training. Another common challenge in feature mapping is handling categorical data, which represents categories or labels rather than numerical quantities. Machine learning models primarily work with numbers, so we need to convert these categories into a numerical format. One simple method is label encoding, where each unique category is assigned a unique integer. For example, reds become 0, blue becomes 1, and green becomes 2. However, this can imply an artificial order or hierarchy that doesn't exist, which might mislead the model. A more robust technique is one-hot encoding. Here, each category is converted into a new binary feature or column. So, if we have colors red, blue, green, we create 3 new columns: is red, is blue, is green. For each data point, only one of these new columns would have a value of 1 and the other 0. This avoids implying any order and is widely used for nominal categorical data. In summary, feature engineering is a vital, iterative process in machine learning, encompassing feature selection, extraction, and mapping. Feature selection helps us choose the most relevant existing features, reducing noise and preventing overfitting. Feature extraction allows us to create powerful new features from existing ones, often reducing dimensionality while preserving information. And feature mapping ensures our data is in a suitable format and scale for our models. This process is rarely a one-shot deal. It requires deep domain knowledge to understand the data, creativity to hypothesize new features, and continuous experimentation to evaluate their impact on model performance. Mastering feature engineering is often what separates good machine learning models from truly excellent ones.